morning.
Morning. Let's start out. And yeah, that's right. We've got 2 more weeks of class left, right? So this week, and then for us, it's just Monday, Tuesday, Wednesday of next week. So let's spend this week sort of learning new material. Roughly speaking, we're finishing chapter 10, and then probably going back and reviewing a few spots that I'll choose. And then next week, we'll review like the whole course for the first 2 days, and we'll do that. Final cumulative assessment, which I hope a cumulative assessment will be kind of nicer for all of you because um, even though it's true we've covered a lot, I think that as the year goes, we get more and more confident with manipulating equations, like getting used to this. So I hope when you see some of that review, it'll start to look kind of friendly. You think about it in the fall, all the way back in the fall, one of the first things we did was like how to solve y equals mx plus b, like y, like 2x plus 3 equals 1, like how do you solve for x? And just think about how far we've come away from that. So speaking about solving equations, let's reorient ourselves like into the moment. So last week we finished off with talking about equations that involve radicals. And let's give you a few of those equations to practice on. So the instructions for each of these problems are please solve the equation. And these are all from the chapter exercise. Just kind of playing out at random. So let's pick maybe square root of a minus b plus 5 is equal to 9. Let's pick maybe 2 times square root of x plus 4 is equal to 16. Let's pick 2 is equal to square root of 4s minus 4 minus 4. And pick one more, so let's do cube root. Cube root of y plus 6 is equal to cube root of 5y minus 2. So let's work on those 4 problems to help review. Let's work on those 4 problems to help review. Working with equations that involve a square root, and then one equation that involves a cubed root. Okay, if I get any time to think, let's go through it. So for first equation, let's try getting the square root by itself. So let's try subtracting 5 from both sides. So square root of a minus 3 would be equal to 4. Now I want to get rid of the square root, so I think of squaring both sides. So I'll take a minus 3 equals 16, and finally a is equal to 13. So there's a reasonable a plus answer. Like I'm writing down my equation, I'm clearly showing each step, subtracting 5, then squaring each side, then adding 3. And well, I guess it's not a plus because I subtracted 3 instead of added. Add 3 to both sides to get a equals 19. Okay, and so then for a second one, similar thing, how do we get square root of x plus 4 by itself? This time maybe let's divide by 2. So dividing both sides by 2, the square root of x plus 4 is equal to 16 over 2. Of course, if two things are equal to each other, I can always do something to both sides of the equation. Those two things will stay equal. This time I'm dividing by 2, you get to cancel. Dividing by 2, 16 over 2 equals 8. So square root of x plus 4 is equal to 8. Squaring both sides would give me x plus 4 is equal to 8 squared, which is 64. And so subtracting 4 from both sides giving me x equal to 60. So in other words, 60 is the thing that you would have to plug in here. 2 times square root of 60 plus 4 is equal to 16. Makes sense because 2 times square root of 64, root 64 is 8 times 2 is 16. You plug it back in, then it scans. So let's look at the third one. Let's look at the third one. So now I've got 2 equals root 4s minus 4 minus 4. So here I'm going to think of adding maybe 4 to both sides. 4 plus 2 is 6, and then adding 4 cancels the subtraction of 4. Give me 6 equals root 4x minus 4. And so why am I doing that? It's again a strategy to isolate the square root and then square it to eliminate the square root. So but first I'll need to add that 4 to both sides. So now squaring both sides, 6 squared equals root 4s minus 4 squared. 6 squared is 36. And that's equal to 4s. Minus 4. Now adding 4 to both sides would give me 40 equals 4 times s. And so you'll see now s has to be 10 because 10 times 4 is 40. You also see that by dividing both sides by 4 would give you that 10 is equal to s. So any questions on that so far? The fourth one's a little different. It's just the cube root. So how do we eliminate a cube root? Well, then you would cube both sides. You would cube both sides. And that would just leave you with y plus 6 equals 5 plus 6. And this one you would try to solve for y. So I want to add 2 to both sides, giving me y plus 8 equals 5. And I'd be subtracting y from both sides, giving me 8 equals 4 times y, and finally dividing both sides by 4, giving me 2 equal to y. So this one I could eliminate the cubed roots by raising to the third power. Now I've got just the inside of y plus 6 equal to the inside of y minus 2. I'm solving for y. Trying to isolate y first by adding 2, then by subtracting 6. Y divided by 4. Is there any question or anything on that? And if we saw questions like that on a final assessment, would we feel confident in being able to do them? Pretty good. We'll talk about inverse functions. Remember from a long time ago, we originally talked about functions. We talked about like relations and functions. So this is the term that everybody, you kind of learn once and then forget about, and but then functions everybody keeps on using. But there is some relation between them. So every function is a relation, but not every relation is a function. So let me write down some pairs of points. Write down another collection. So 1, 2, 3, 1, 3, minus 1, 4. And so when you write down a collection of pairs of points, this could either be a relation or it could be a function. Like these are your x values, and these are your y values. So if you put it into a chart, you've seen this represent functions, relations with charts, and this would look something like 1, 2, 2, 3, 3, minus 1, 4, 5. You put this into a chart, and it would look something like 1, 2, 2, 3, 1, 3, 1, 2, 4. Now, one of these represents a relation, and one of these represents a function. So whether you put it in coordinate pairs or charts, this collection of 1, 2, 3, 4 points, whether you put it in coordinate pairs or a chart, this collection of 1, 2, 3, 4 points. So the first thing I'll do, just by way of review, since the term is coming to a close anyway, so why not just review some material? Which one is a function? And I mean, they're both relations, but which one is a function and which one is a relation but not a function? So which one is a function, which one is not? So take a moment. And this one I'd like an answer on. So I'll ask you, if you're online, please chat me what your answer is. And if you want to look up what is a relation, you can find that in the book or just Google it. And that'll help you do some research, like what's the difference between those two things. So if you're online chatting, you can say, is the first one a function or is the second one a function? Give you a few more minutes, please chat me. Which one is the function? Okay, so for some reminder maybe about like the terminology, you think about you think about taking a function and breaking it up in its domain and range. Remember, the domain is like your collection of inputs. The range is the collection of outputs. And for a function, functions can look something like this. Each individual point in the domain goes to one point in the range. And so, actually, let's just take this one. I can write down the points 1, 2, 3, 4, and 1 got sent. And well, what are the values of the range? It's like negative 1, 2, 3, 5. So for the first one, 1 got sent to 2. That's sort of what I'm doing with this chart. And like 2 got sent to 3. 3 got sent to -1, which is fine. And 4 got sent to 5. So each different point in the domain, each point in the domain got sent somewhere in the range. And it's fine if you double up in the sense that like if we took another point, like I did 5, 3, like I made another point in the domain and sent it to 3. That's allowed. So this is still a function, like, because it's fine for 2 points in the domain to have the same y value. It's just that when you pick 1 point in a domain, it can only go to one place. That's what makes it a function. Whereas for a relation, if you have something like that, then this is no good because you've got 1 point in the domain going to 2 different places. And that's allowed for a relation, but it's not allowed for a function. So a relation is just like any collection of coordinate pairs that defines a relation, like x and y are related to each other. But the difference is that while in a relation, one x value can go to different y values. Like you've got one going to 2 and one going to 3. That's allowed for a relation, but it's not allowed for a function. So if I were to draw this like in the visual chart, like I did here, with the domain being 1, 2, and -1, and the range being like 2, 3, 4. So if I draw what, like 1 is related to 2, and -1 is related to 4, and then 2 is related to 3, and I've also got 1 related to 3. So the thing that makes this not a function is the fact that 1 is going to 2 different places. You can also see that visually by saying, like if you look down at these x-coordinates, as soon as you notice 1 appearing twice and having different y values, that tells you that that one can't be a function. So what we're getting into is like what's the inverse of a function? Some functions have inverses, other functions don't. Let's talk about it. But first, let's figure out like what's an inverse. So if f of x is equal to y, you know, like this is the input. X is the input, and y is the output. Like a function is like taking something in and putting something out. I'll give you 2 examples of functions here. So let's take f of x equals 2x plus 1. So this f of x is a linear function. And I'll take another function called g of x. And that one I'll just say like x squared. And this one is an example of a quadratic function. And more review of terminology, these are both polynomials. Polynomial just means something that looks like 1 plus constant times x plus constant times x squared plus something times x. So but whatever. So here's a function, there's another function. So one input goes to one output. And so for instance, like you could have what, like f of 0 equals 1, so x equals 0, y equals 1. You can have f of 1 is equal to 3. So how am I getting that? Substitute in x equal to 1, 2 times 1 plus 1 is 3. And so the inverse function, you write it by putting a -1, call it f inverse. So that the function takes x to y, the inverse function takes y to x. So like the inverse of 1 would be 0. Inverse function of 3 would have to be equal to 1. So like if your function was given by like 0, 1, 1, 3, 2, 5, then your inverse function, all these would be swapped, right? They would be, your inverse function would have to take 1 to 0, since this took 0 to 1. It would have to take 3 to 1. Since this one took 1 to 3, it would have to take 5 to 2. Since this one took 2 to 5. So the inverse function, like intuitively, it undoes whatever the function does. So if you've got this one sending x to 2x plus 1, you can, there is a formula for the inverse. So like you can think through, like how do you undo this? What would you do? Like subtract 1 and then divide by 2? Would that make sense? So if you're lucky enough to get your function as a list of coordinate pairs, you can just switch the x and y values. Regarding the formula, that might be something we have to talk about a little bit more. But that's what an inverse function is. On the other hand, this is a function where apparently there's no inverse. Gotta be like a little bit careful about that, because if you graph g of x, look at these two places. You've got g of minus 1 equals minus 1 squared, which is equal to 1. And you've got g of 1 equals 1 squared equal to 1. So you've got that's this point and that point. So this is the point x equals 1, y equals 1. This is the point x equals minus 1, y equals 1. So that's like the symmetry of this graph, right? You switch over the y-axis, it stays the same to whether you're looking at 1 or negative 1. It's the same because you're squaring it. So if there were an inverse, then the number 1 would have to get set to 1, right? Because g of 1 equals 1, so g inverse of 1 would be equal to 1. But it's also true that negative 1 gets sent to 1. So if there were an inverse, it would have to be true that g inverse of 1 is equal to negative 1. 1 would have to go to negative 1, and 1 would also have to go to 1. So it would have to be true that the inverse sends 1 to negative 1, and the inverse sends 1 to 1. And so that's not a function, it's a relation. So there's no inverse function to this. Generally speaking, whenever it's possible to draw a horizontal line like that and hit the function at any 2 points, it's not going to have an inverse because of the fact that the inverse function would have to send one single y value. So this is the one single y value, like the number 1 was the one single y value for these 2 points. You've got 2 points with one y value at different x values. So the inverse function would have to take that one y value and send it to two different places. So and that's called the, well, I'll write it down later, but that's called the horizontal line test. Whenever you can take a horizontal line and draw through a function, draw through the graph, you're not going to be able to have an inverse. Do a little bit of practice. Actually, let's focus in on this problem. Let's see. See if we can take some special examples. So let's take. So then this game is going to be called, like, can we find the inverse function? So I'm going to take f of x equals x, g of x equal to x plus 1, and then h of x equals 2 times x, and then j of x will finally go up to x plus 1. So please, like, do these in order for each one. For each one, an inverse function exists. And what I'll ask you to do is please take a few moments and can you find like a formula for the inverse of each function. So remember that if f of x equals y, then the inverse would have to take y into x. So maybe I'll even write the variables. So f inverse of y. So the input and the output get switched. And think of this if you like, you know, you can write y equals f of x, you can write y equals g of x. So your x and y value are getting switched to find the inverse. So take a few moments for each one. Find the inverse function. I'll give you more time, but I'll jump in and give you a hint just so like you can sort of see the game a little better. So what's happening here? So you've got x and y, and apparently y is equal to x. So if I'm writing y equals f of x, I should be writing x equals inverse function of y. So what's the inverse function? So this is y equals x. This one is just x equals y. So f inverse function of y is equal to y. So if f of x equals x, then f of y equals y. It makes sense because f of x is not changing the value. So the inverse also does not change the value. If you graph that function, remember y equals x. Looks just like this. It's the collection of all coordinate pairs that are equal to themselves. Minus 1, minus 1, so on and so forth. So if you write this down in the list and switch the two, nothing changes. So if x sends, so if this function sends 1 to 1, then when you reverse it, it's still sending 1 to 1. So if I write y equals x, and this time I'm just writing x equals y. Here's the first time where something is a little bit different. So if I take in y as a function that adds 1, the inverse, what would you have to do to undo that? So if y is equal to x plus 1, then x is equal to something. So that's my little hint, and that's the first one. So what are the next three? Give you another minute or two. After giving you some time to think, starting to see a pattern here. So this one was if y is equal to x plus 1. So in order to get, if I plug in x and to get y, I have to add 1 to it. So y is equal to x plus 1. I want to think about oppositely. So what if I plug in y? How do I get x? So if I'm plugging in x plus 1, plugging in y equal to x plus 1, plug in x plus 1, how do you get x? Well, you would have to subtract 1. So this would be x equals y minus 1, which starts to make perfect sense when you think about it, because if you look at this equation, y equals x plus 1, I can just subtract 1 to get x equals y minus 1. So you start to see that what I'm doing here is I'm given something that's solved for y. In order to find the inverse, I just need to solve it for x. And that pattern will continue because for this third one, if y equals h of x, then x equals h inverse of y. And so how do I get x when I plug in y? Y is equal to 2x. So how do I get x when I plug in 2x? I would need to divide by 2. In other words, how do I solve this equation for x? I would need to divide by 2. So x is equal to y over 2. X is equal to y over 2. And then how do I undo what is done by this function? So this is 2x plus 1. So if x is the input, then y is multiplying that input by 2 and add 1. If 2x plus 1 is the input, if y is the input, how do I get x? I think I need to subtract 1 and then divide by 2. In other words, if I solve this for x, I'm going to get, well, y minus 1, and then divide everything by 2. It's equal to x. My coffee cup out of the way there, so it's not blocking the screen. The board. So this is telling me that if y is equal to 2x plus 1, then the inverse x would have to be equal to, what is it? I'll write this as y over 2 minus 1/2. In each case, you're switching x and y. So switching x and y, that's the same thing as reflecting over the line y equals x. So when y is equal to x, then x is equal to y, you're reflecting over that line, but the function is the line, so nothing changes. So that's kind of fine. When you've got, let's think geometrically, so when you've got y equals x plus 1, so that's the straight line translated up by 1 unit, then you're going to have x equal to y minus 1. So here's the line y equals x, the dotted line. What happens if you flip this over the axis? You're going to get that. Right? Isn't that kind of looks like a road? So you're going to, if you take this and reflect it over the line y equals x, reflect it over that mirror, then that's the image that you're going to get. And that's given by x equals y minus 1. So what you can do for next time, for tomorrow, is you can think about, please, can you draw the graph of the function and its inverse for these two? And I'll show you them on Desmos at the beginning of class tomorrow. So that's it for today. We'll continue with inverse functions, section 10.4, tomorrow online. Thank you, everybody, for your time and attention.
Thank you.